Hello, hello, hi everyone. Okay, so honestly, what happened was I got a notification on my laptop that said that my memory was full as of recording this video. So I made some space and we're gonna keep going on. So no time hopefully will pass between you, but for me it was a bit of it was a bit. So let's see. Okay. So just to recap, right? We were talking about evaluating this limit, and we saw that when we just actually plugged it in, that we got a 0 over 0, and that's a no, we don't like that. But in revealing that the top part was 0 when we plugged in 3, I'm sorry, negative 3, then we know that this expression can divide out that polynomial. So x plus 3 can divide out this polynomial, and we get a factor of x plus 2. So we know x plus 3 times x plus 2 gives us that guy. Rewriting that top polynomial, we can see that we can cross out x plus 3, and we're left with x plus 2. Now plugging in negative 3, we got negative 3 plus 2. That's going to be just a negative 1. And that's going to be our limit. All right. Over here next, we have, let's plug everything in. We have, square root of 3 plus 1 minus 2 over 3 minus 3. Square root of 4 minus 2. I can already see where this is going. And yeah, that's also going to be 0 over 0. We do not like this, right? Oh no. But, we can mess with it with rationalization. So let's go ahead and do that. So I'm going to multiply this whole thing by rationalization. So I'm going to multiply it by the square root of x plus 1 plus 2 over square root of x plus 1 plus 2. I get x plus 1 minus 4, because it's 2 squared, over x minus 3 as a factor in square root of x plus 1 plus 2 as a factor. That top part just becomes x minus 3. And look, we have something that we can factor out of the top and the bottom. So we just have 1 over square root of x plus 1 plus 2. Now we can plug in x to be 3. We got 1 over square root of 3 plus 1 plus 2. So it's going to be 1 over square root of 4 plus 2. Uh, 1 over 2 plus 2. 1 over 4 is our limit. All right. Next one, same thing, plugging it in. Yeah, we're definitely gonna have the bottom. The bottom will be 0 for sure, but let's just evaluate the top. You never know. Yeah, the top's gonna be 0 as well. And again, it's a no-no. But multiply the conjugate. Square root of x plus 3 minus 2 over x minus 1 times square root of x plus 3 plus 2 over square root of x plus 3 plus 2. X plus 3 minus 4 over x minus 1, square root of x plus 3 plus 2. We see the top part just becomes x minus 1 over x minus 1 times square root of x plus 3 plus 2. And that's going to be 1 over square root of x plus 3 plus 2. That's 1 over 4. Okay. All right. Or no, it doesn't equal 1 over 4. I'm going to do an arrow because that's not the same thing. Okay. All right. Making sure. Okay. Did you all see my forehead when I did that? No. Okay. There, that's my forehead. Eey. Let me see. Let me see. Ugh. What are you seeing? Oh, you're not seeing my forehead. You see my eyebrow? Oh, that's weird. Okay, sorry. Sorry. All right. Now let's practice this idea with piecewise functions. So for piecewise functions, it's not too different. The only thing we really have to evaluate is what the left and the right of a variable look like. So We're going from this f of x, we're going to 2 from the left. So that means which function are we following? Are we following this one on top or this one on the bottom? Well, via this inequality, we're going to values to the left of 2. This is the values left of 2, this top one. So it's x squared. So that means we can just plug it in to be x squared. And that's going to be, or well, x to be 2, we plug in for x squared. I should be more specific. So that's just going to be 4. Okay? And then after plugging that in, we do the right side. So that tells me we're going to pull this guy over here. So to the right, that's plugging in x to be 2, and that's going to be 4 as well. So it's the limit of both, well, 4, right? So it seems like the piecewise function didn't really mess with this too much, but what about over here? So when x goes to 1 from the left, we are following this top polynomial. So as it seems as this function would go to 1 from the left, right? But just go into 1, we could plug it in using the, I already forgot the name, wait for it, the substitution theorem. We can just plug that in to be 0. Because 1 squared minus 1, 1 squared is 1, 1 minus 1, 0. How about from 1 to the right? So we'd be using this guy. So that's going to be, just plugging it in, it's going to be 2. So what's the limit as x goes to 1? Well, that limit does not exist. Why? Off the technicality that those two limits from the left and the right do not match. Okay. Now we're going to talk about some more limits at infinity. So just a quick starter for this. If the degree of the numerator is less than the degree of denominator, the function is bottom heavy, and its limit at infinity is 0. If the degree of the numerator is equal to the degree of denominator, the function is balanced, and its limit is the ratio of the leading coefficients. Then lastly, if the degree of the numerator is greater than the degree of denominator, then the function is top heavy, and the limit is at infinity. Or limit at infinity is either positive or negative infinity, or it does not exist. So let's go ahead and talk about these guys one by one. So we're going to start here. And for here, this tells me that that power is 1, and I mean that degree is 1, that degree is 2. So that means the degree of the numerator is less than degree of denominator. So that limit will be 0. How about over here? Those degrees match. They're both 3, even though they're misplaced, they're both 3. So the leading coefficient at top is 1, the leading coefficient is the bottom is 2. So the limit is 1 over 2. Same thing over here, that's 5 over 2. They both have a degree of 2. Over here, the limit of the top is bigger. So that means we're going to be paying attention to this value on the top. Now, this is as x goes towards negative infinity. So as x goes towards negative infinity and x to the third goes towards negative infinity, that will be a limit of negative infinity. Over here, the top has a degree of 4, and similarly, it's also negative. So it's going to be a negative infinity again. And over here, degree of top and degree, and as this expression goes towards negative infinity, this guy will, even though this will force it to be positive, like here, that force to be positive, that multiplying by a negative ruined it. So it's also going to be negative infinity. Now, a couple of theorems we want to introduce. First, the power limit theorem. If r is a rational number, then as x goes towards infinity, 1 over x to the power of r will be 0. Now, if r is a positive rational number, such that xr is defined for all x, then as x goes towards negative infinity, 1 over xr will also be 0. This is just a sort of neat little trick that we're going to force to appear. So when we take these infinite limits, we can deal with those expressions a lot easier. Now, keep in mind that we've upped the difficulty from here to here to be limits of infinity. So that doesn't mean that we can use all power laws. We can use all of the ones except for limit laws, excuse me. So we can use all the limit laws except for the power law and the root law. However, what we can use is the following law. If we know that within a function that f of x reaches some finite limit, then, and what it's being plugged into is continuous, then we can go ahead and just say that the limit of this, regardless of it being infinity or not, will just be that value taken to that limit. So g of L. Again, if the limit as x goes towards an infinity of f of x is equal to L, and g of x is continuous at L, then the limit as x goes towards an infinity of g of f of x will just be g of L. Okay? So this is going to help us a lot as we analyze these limits. So let's start off with example 13. So example 13 reads this fraction. Now keep in mind, we technically already did this one, but it's just important. What I'm going to do is I'm going to practice using, with this guy, the power limit theorem. So we know that 1 over an x to the power of an r will make that limit disappear into 0. So what does that mean? So that means I can manipulate this such that I can factor out an x squared from this expression. So I'm going to rewrite this expression to be x squared, parentheses 5 minus 3 over x squared, and then x squared, and then left with 2 plus 7 over x squared. And I'm going to go and cancel out those x squares. I have 5 minus 3 over x squared over 2 plus 7 over x squared. Now remember the limit, the rational root. What did I call it before? I already forgot. The power limit theorem. These guys, as x goes towards infinity, will disappear to 0. And these are constants. So that means if I do some limit laws, and I apply the limit here at this one, I will just practice doing piece by piece first. Of 5 minus the limit as x of infinity of 3, 1 over x squared. Why did I draw that line there? Let me go ahead and erase that line. So that line could be misleading. Over the limit as x goes towards infinity of 2 of plus 7 of the limit as x goes towards infinity of 1 over x squared. Both of these limits will be 0. So you're left with 5 minus 3 times 0 over 2 plus 7 times 0, which is just 5 over 2. Which is what we said the limit was when we were talking about the top-heavy, bottom-heavy, and balanced ideas. But it's just important that we redo it just to be safe. Okay. Now, next. For this guy over here, we see that we're going to have some confounding ideas. Because technically speaking, right, this term will be forever increasing, even as x goes towards negative infinity. And this term is just the x slope. So as x goes towards infinity or x goes towards negative infinity, it's going to fluctuate. So this really doesn't tell us anything. And we can't really use limit laws because we're just going to get a bunch of infinities stacked and timing each other, which isn't going to help us at all. But what we could do is we can go ahead and manipulate this a little bit to get something more palatable. first thing I want to do is I want to manipulate what's inside the square root so I can prep it to use that power limit theorem. Now from here, I can technically factor out x squared like what I did for these top guys. So I'm going to factor out x squared. Within that square root, we have x squared times 1 minus 2 over x plus 7 over x squared plus 7. Plus 7 plus x. And then I'm going to go ahead and take out that x squared. Now keep in mind, due to the technicalities, we don't know if x is positive or negative because we know that for this, it can either be positive or negative, right? Because when a value is squared, it loses its negativity. So we have to assume its negativity. So I'm going to write it like this. Now, from this point on, I have to use the fact that my limit is as x goes towards negative infinity. So that tells me that before it escaped in here, x was actually negative. So because we're dealing with this limit over here, I'm going to turn this, or here, let me write it like this. It's because of this, I'm going to turn this into negative x. Square root of 1 minus that 2x plus 7x squared plus x. The reason why I do negative x is because at the end of the day, it's supposed to be an absolute value, right? When you factor out that x squared under that square root, what's supposed to come out is a positive value. But we know x will be negative because we're going towards the left. So accommodate for that, we're going to multiply x with a negative. And that way, this will force that value to be positive. All right, let's see. Now from here, what I'm going to do next is factor out the x. I think I'm going to run out of space. Let's work. I'm going to go ahead and do a little bit more color coding. Let's work over here. We have negative x. Okay, I'm going to do a little star. Negative x square root of 1 minus 2x plus 7x squared plus x. I'm going to go ahead and factor out x from here. I get x parentheses negative square root of 1 minus 2x plus 7x squared. And then I'm going to go ahead and do plus 1. Okay? So from here, I need to multiply this by the conjugates. The reason why I'm doing this is because I'm still having conflicting terms, right? At the end of the day, if I take this limit, I know that if I take the limit of here and here, that's going to be 0 times x, which isn't really true because we saw here that, well, that limit's not really bounded by a 0. So I do have to keep evaluating this a little bit more. So let's use the conjugate to evaluate it a little bit more. X times, actually on my solutions, I have I'm going to try different conjugates. So I have in reverse, I have 1 minus the square roots. So I'm going to go ahead. Times, plus 1, excuse me, times, there's square root of 1 minus 2x plus 7x squared, then minus 1. Okay? And then what you do top, you have to do to bottom, because at the end of the day, we're abusing the fact that we're multiplying by 1, even though we're not literally multiplying by 1. Okay. All right. Let's do that. We have an x. I don't know why. Let's put on the top. Actually, no, let's leave it on that side. I have a feeling it's going to be on side. So these two multiply each other. That gets rid of the negatives and the square root. So we have 1. Yeah. Then we can still do it. 2x plus 7x squared. And then plus 1 minus 1. So it's going to be a -1. And on the left, we have negative square root of 1 minus 2x plus 7x squared minus 1. Okay. So that's going to cancel out here. And then I'm going to go ahead and distribute that x. So I'm left with -2 plus 7 over x over negative, and I'm just going to rewrite the whole thing. Now, this is where that composite limit rule I told you about is going to come into play. Because for the top part, I can already evaluate the limit of the top part. That top part's limit is going to be -2. But the bottom part, the limit doesn't exactly escape into the square root. But technically, if we were to just take out the square root mentally, we can see that the limit of the inside will just be 1. So using the composite rule, implying that they're all equal, I can just sneak it into here because this limit is defined. We know limit as x goes towards -infinity for this because of the rational root ideas will simply just be 1. So I can rewrite that because of limits used. I'm going to write limits used here. I get negative square root of 1 minus 1. Okay? Well, square root of 1 is just 1. And then -1 minus 1 is going to be -2. So -2 divided by -2, that's going to be a 1. So that's my answer over here. Okay. All right. Next, let's do example 15. For this one, I'm going to already prep that square root by factoring out that x squared like what I did before. I'm going to skip a couple of steps here. I'm going to go ahead and do the absolute value of x square root of 4 plus 1 over x squared over x plus 1. Now, because I'm going to the positive side of x, I can turn that absolute value here into just a classic x. And then I'm going to go ahead and factor out x from this whole fraction. So divide this thing by x, divide this thing by x. I have the square root on the top then. And then I have 1 plus 1 over x. Take the limit as x goes to infinity. The power theorem here, that's going to be the square root of 4. Our limit used here, limits used here. That's going to be square root of 4 over 1. Square root of 4 is 2, so 2 over 1, 2. All right. One more time. We have, for example, 16. We have this one, we can't really prep too much here. What I am going to do, because I still want to be able to divide by an x, I see that I can't really divide by x squared because that won't escape here. But what I'll divide by is actually the square root of x. So when it escapes here, it can eliminate this and make it a bit more palatable. The goal with this whole dividing by x thing is that we want to make sure that there is no numerator with x on it. That everything is a fraction of something divided by an x power. So we can, when taking an infinite limit, make it 0. And that makes it streamlined for us. But we can't just divide anything willy-nilly by, a powerful x. We have to do it within reason, and we have to do it to where it's mathematically sound. And we're not just getting, 0 divided by 0. Okay. So for here, I'm going to go ahead and divide by the square root of x. I have 2x plus 1 over the square root of x. And then I have the square root of x plus 1 over the square root of x. Messing with it here, I get 2 square root of x plus 1 over the square root of x. And then in here, I get 1 plus 1 over x. Now, for here, you can't really take out the limit anymore. If you ask yourself, well, this is still an x with a numerator on top, and you decide to just actually factor out x instead of the square root of x, you'll see that you'll get 0, or divides by 0, which is not proper. So this is the best we can do. And we can still take these limits. As the limit of the top part as x goes towards infinity, we can only really simplify that top part a little bit. We still have the limit as x goes towards infinity of the square root of x. And that part just became a 0. The bottom part, because of that composite function rule, and because of the rational root theorem, we get the square root of 1 plus 0, I guess, right? Well, we know the top part and the bottom part can be simplified to just 2 as the limit as x goes towards infinity of the square root of x. But we know that if we follow that square root function as x goes towards infinity, that's just also going to go towards infinity. So from here, we are forced to say that the limit as x goes towards infinity for this function is just infinity itself. Now keep in mind that you want to make sure that you evaluate all options possible. If you're dividing by 0, you've gone too far. But if you're not dividing by 0, and you do have, some other attributes to deal with, or some other, explanation, some sort of mathematical thing you can do, then you need to do it. Now, granted, is there a concise way to do all of these? Yes and no. I kind of structured it in a way to where I would think about it. So that's why I started first with this whole top heavy, bottom heavy, and balance portion, where that's really easy to just figure out. You go boom, boom, boom. But technically, sometimes we're dealing with an expression that just looks like a confused polynomial, and then that's not that funny. I don't know why. But and then also we're dealing with expressions that have that square root attached to it. So just keep that in mind. At the end of the day, you can also force the power limit theorem, but within reason. Okay, keep that in mind. Oh, and then also this composites law. Because remember, once you start taking x to be infinity, you can't directly use the power and root law. You have to do it a little bit differently then. All right, last part of this lecture. If any of the following conditions hold, then the line y is equal to L is a horizontal asymptote of f of x. So that means if that limit at infinity is an actual defined numeric value, then that's going to be a horizontal asymptote. So at the moment, determine if any horizontal asymptotes of example 13/16's function. Okay, so for this one, example 13, that one's actually pretty straightforward. It was a balanced equation. So that means it didn't matter if we were going from the left or from the right. That's just going to have that value 5 over 2. So that means that horizontal asymptote is 5 over 2. regardless of we're taking the negative limit or the positive limits. Here, though, we do have to address this. Because remember, we use the fact that x goes towards negative infinity right here at this point, and we turn into negative x. So that means for this, let me use a different color. And for this, we should jump right here. But then make it positive, since now we're addressing it the other way. X goes towards infinity. Because before with this, we can easily say that a horizontal asymptote is the y is equal to 1. And that's just using the previous one. But it's this and this. So we have to double check the other way as well, which is why I wrote it like this technically. Okay. We're dealing with a positive limit, a positive infinity, so that becomes positive. So we're just dealing with x of this square root. Oh, I wrote 2. It's supposed to, 7. It's supposed to be 2. Plus 7x squared plus x. Factor out the x here. We have x of that square root. Again, here we have a similar issue with just, the limit being going towards infinity, which doesn't really tell us much, especially when over here we got, a confounding negative infinity and positive infinity idea. So we want to make sure that we evaluate this limit correctly. So let's go ahead and multiply the conjugate. If we get infinity again, then that's going to be the answer. The answer is infinity. They don't always have to have an alternating asymptote, but we should double check it anyways. So multiply the conjugate. We get square root 1 plus 2, or 1 minus 2x plus 7x squared plus 1 times that square root. Here, I'm not going to write it again, just put minus 1. And divide by that square root again, minus 1. So that becomes x times 1 minus 2 over x plus 7 over x squared plus 1. And then divided by square root 1 minus 2x plus 7 over x squared, and then minus 1. Okay, so let me just check my solution really quick. Okay. Okay. All right, then from here, we can go ahead and do this, and we get 2x minus 2 plus 7 over x over 1 minus 2 over x plus 7x squared minus 1. Okay? Well, if you check the top and the bottom, we do have an issue. The issue being that if I evaluate the limit as x goes towards infinity for here, this expression will be 0, which we know we cannot divide by 0. So, if that's the case, then we could force another x to happen. But we can already sort of see it here that if we fix this any sort of way, we're just going to have a forever increasing variable. Go back to here, where we kind of clock that this is a positive number, plus 1. So positive times x. As that goes towards infinity, right? That means that a positive number times infinity is just going to still be infinity. It's going to keep going on forever, forever. So that tells me that there is no other result here, and that limit's going to be infinity as well, and that we really can't do much after that. Okay? All right. Next, let's do example 15. I mean, we still have the horizontal asymptote from this part, but it's important that we just pretend like there's two, because spoiler, I did put one where there is two horizontal asymptotes. Okay? Um, let's see. For here, we have the first horizontal asymptote from the previous one, that y is 2. Let's check it over here, and for that, again, I'm going to copy this idea over here of factoring out that absolute value. So we have absolute value of x, square root of 4 plus 1 over x squared over x plus 1. And this time, it's x goes towards negative infinity. So that means we should write negative x, square root of 4 plus 1 over x squared over x plus 1. And I'm going to factor out x from this. So we have negative square root of 4 plus 1 over x squared over 1 plus 1 over x. Take the limit of both of these guys. We will get negative square root of 4, or let me write limit used here, over 1. And that's going to be negative 2. So we do have a second horizontal asymptote. Y is equal to negative 2. Now, 16, I'm going to tell you right now, is a trick question. The gimmick with 16 now is that we are doing x going to negative infinity. And we notice that this expression here, if we jump past negative 1, that's going to be undefined. So x does not exist into negative infinity. So therefore, this limit does not exist, and we're only left with one horizontal asymptote. Or, oh, I'm sorry, we're left with no horizontal asymptote, because even here, we didn't get an explicit value, we got an infinity. So therefore, there's no horizontal asymptote with 16. All right, now, just a brief thing. Oh my gosh, I just realized for the vertical camera, the avatar was turned off. I'm so sorry about that. Okay, all right, just turn the avatar back on. Sorry about that. Okay, let's see. Now, what was I gonna do? Okay, I wanted to show you all, just briefly, how it could look for these equations on a graphing calculator. So let's go ahead and share that screen with you all. Give me a second. It's not letting me, hold on. Where is it? Okay, found it. All right. Okay, let me just add it here as well. Okay, give me a second. Then I need to fix it here as well. Okay. Or actually, maybe like that. Okay. So first equation reads 5. All right, here, let me do a fraction first. We got 5x squared minus 3 over 2x squared plus 7. Okay, so we see here this weird split, but that if I mark it as f of x and I go to a positive value, f of, let's see, 10, 100, 1,000, etc., my value gets close to 2.5, which is 5 divided by 2. If I do a negative, it will also stay to 2.5. All right, next. Let's get rid of this guy real quick. Okay. If I do g of x as the square root of x squared minus 2x plus 7, and then later I add an x, we see that as our values were correct, as we go towards the left here, or let me do the right first, I guess. As we go towards the right, it seems to just increase forever. But as we go towards the left with a negative number, it seems to go towards 2. Wait, let me see. Is this 2? Wait, how do we get 2? Let me see quick. Maybe my key is wrong. Um, let's see, did I make a mathematical error? I am human, so I am prone to that. You see? What? Even visually, let's start with -1. What the heck? What was that? That's a weird typo. I don't know how that happened. Okay, but we now see it's 1. Okay, that was strange. Okay, let's keep it going. Okay, and then oh no, I already showed it for positive, right? That we see that it goes towards infinity. Okay, all right, next, let's do h. Go towards square root of 4x squared plus 1 over x plus 1. We see that this indeed has two horizontal asymptotes. We can see that visually here, but as we approximate it, we should see that if I keep increasing to right, I get a number close to 2. And if I keep increasing it from the left, I get -2, which are the values that we ended up getting. Okay, last one. Let's do j of x, just to be quirky. Or I don't think it's gonna let me do j. Okay, let's just do our f of x and then delete this f of x. Okay, we have 2x plus 1 over the square root of x plus 1. Okay, so here you can already see that the negative limit does not exist because it just as here I could do -1, it's already undefined. And if I keep going, it's still undefined. But if I go to the right, I keep getting just this really high number. Okay. All right, guys. Sorry for that little Desmos side tour, but I just wanted to make sure that we got um this part, you know, done with. Sorry for the technology hiccups. I'll try to be better about that. Let's see. Is there anything I want to say I skipped? I want to make sure that we're aware of what happened here. Okay? Just keep that in mind, right? At one point, you could even see it like right here, like, oh, this is just going to be, increasing, infinitely. But it's a good to explore the conjugate as well, just to double check. Now, I'm gonna be transparent. I probably wouldn't give you this kind of a, exploratory problem on a test, maybe on a homework, but probably not a test. Or if I do, I'll tell you something to the effect of like, you should get two horizontal asymptotes. Check when x goes towards infinity. Or you should get one horizontal asymptote. No, well, if you get two horizontal asymptotes, you're probably checking both infinities. But like if I'm saying, I'll probably give you like something that won't dissuade you, because even though it's a time test and you can take it whatever, I still like to keep it within like a certain expectation. Okay. All right. Let me know if you guys have any questions, okay? Because this one was a bit tricky. I did come into here expecting you to know. Let's see. I know I expected you to know, factoring ideas. This absolute value idea kind of does come out of nowhere, maybe, but we just have to remember that, when you take anything out of a square root, right, that value is technically introduced as positive. So keep that in mind. Or if you're assuming both, sometimes when we do a square root, we remember the positive negative idea. It's to account for that what if. What if it was positive? What if it was negative? So keep that in mind, okay? Because any constant that escapes an expression within the square root has to be positive, because we know that for a square root, the inside of it cannot be negative. So just keep things like that. I'm hoping those are clicking with you all. It's kind of hard to be honest because it's a virtual class. So I really need you guys to watch these videos and to double check everything and make sure that if you don't understand something, we can go over it again. I do have a phone. I have the fold, so I can literally open it up and like take notes and write you like a little PDF if I need to, but you just gotta let me know. All right. I wish you all the best. Have a good one, guys. All right. See you in the worksheet video. I'm probably just gonna record that right now. Bye bye.